Good day, everyone. Welcome back. I hope you all had a productive break. Today, we are diving deep into Unit 5, specifically focusing on the fascinating world of vibration pickups. As we discussed previously, understanding and controlling the vibration and noise is very crucial in mechanical engineering. To effectively analyze and mitigate unwanted vibrations, we first need to see a way to accurately measure them. That's precisely where vibration pickups comes into play. This unit, vibration pickups, will equip you with knowledge to understand the principles behind these essential sensors, explore different types available, and learn how to select the right pickup for various applications. We will delve into the mechanisms, sensitivities, and factors that influence their performance. So get ready to explore the devices that act as our ears and feelers in the realm of mechanical vibrations. Let's begin our journey into the world of vibration pickups. So, as we begin to explore the different type of vibration pickups, it's important to understand that many of the most common ones operate on the principle of seismic instrument. This slide illustrates a simplified schematic of such a device. Notice the key components here. We have a suspended mass denoted by M connected to a cage or housing through a spring represented by K, and a damper represented by C, often visualized as a dashpot. The crucial point here is that the bottom end of both spring and damper share the same motion as the cage itself. Imagine this box or cage being attached to the vibrating object we want to measure. Now, when this object vibrates, this cage and consequently the bottom end of the spring and damper also move. This vibration will excite the suspended mass. However, due to its inertia, it is resistant to change in motion. That is, the suspended mass will tend to lag behind the motion of this one. The key measurement we are interested is in the relative displacement of mass and cage. This relative displacement is simply the difference between absolute displacement of the mass x and absolute displacement of the base. Mathematically, we can express this as z equal to x minus y. Understanding this relative motion is fundamental to seismic vibration pickups. By measuring this relative displacement, we can infer the characteristics of original vibration. As we established the relative displacement between the suspended mass and cage z, that is our key variable. Now consider a scenario where the vibration we are trying to measure, that is y of t, is going to be in the form of harmonic motion. So we are representing this as y sin omega t, where y is amplitude of the vibration and omega is angular frequency. To understand how the relative displacement z behaves in response to this input vibration, we need to look at the equation for this suspended mass M. Applying Newton's law, considering the forces acting on the masses, spring force, damping force, and all the inertia forces, we can arrive at this differential equation, that is mx double dot inertia force plus damping force plus stiffness force. Here x double dot represent acceleration of the mass, x dot, y dot and all represent velocity of the mass and cage respectively. This is the relative displacement. So we can rewrite the equation in terms of z by substituting z equal to x minus y. It will be rewritten in this form. Then the second derivative of this y sin omega t, we can substitute here y double dot, that will become as omega square y sin omega t, minus minus sign will get cancelled out. So at last we are getting a equation of motion, that is mz double dot plus cz plus kz equal to m omega square y sin omega t. This is second order linear non-homogeneous differential equation. The right hand side represents forcing function due to the base excitation. Our goal is to find steady state solution for this harmonic equation. Let we assume the steady state solution z of t, which describes sustained relative motion of the mass after any initial transient effects have died out. For a sinusoidal input, we can expect a sinusoidal steady state output at the same frequency, but possibly with a different amplitude and phase. Therefore, we can assume steady state solution itself, that is z of t equal to z sin omega t minus pi, where capital Z is the amplitude of relative displacement and phi is the phase lag between relative displacement and base excitation. Let me solve Z in the next step. Now we have the solution for the equation of motion, that is the steady state solution. We can actually solve for the amplitude of the relative displacement Z. After solving the differential equation, we find that amplitude of the relative displacement Z is given by this equation, and further simplifying by dividing numerator and denominator by omega n, that is r equal to omega by omega n. So if you are substituting by omega n, here this will become as r square. So we are getting the same equation in the form of r square, where r equal to omega by omega n. To make this expression more insightful, we are also using the damping ratio. The natural frequency is the frequency at which the system would oscillate if there were no damping, and it is defined as omega n equal to k by m. The dimensionless ratio we can arrive, that is z by y, will be represent amplitude response of our seismic instrument. It tells us how the amplitude of the relative displacement compares to the amplitude of the input vibration at different frequencies and for different damping ratios. So you can see it here. The graph on the left illustrates this relationship. It plots the magnitude of y by z or z by y as a function of frequency ratio omega by omega n for various values of the damping ratios. Observe how the response varies with frequencies. At low frequency, small r, the value of z by y also very small. As the frequency approaches the natural frequency, that is omega equal to omega n, we see there is a significant peak, especially for lower damping values. This phenomena is going to be called as resonance. At frequency much higher than the natural frequencies, the ratio tends towards 1. This frequency dependent behavior is what allows us to use the seismic instrument for different purposes. Notice the indicated range for accelerometer and vibrometer at different frequencies. We will discuss this in more detail, how the operating frequency range relative to the natural frequency and the damping ratio, whether a seismic instrument is best suited for measuring acceleration, velocity or displacement. Alright, we have looked at the amplitude response of our seismic instrument. Let's turn our attention to the phase relationship between the input motion and output relative displacement. As we mentioned earlier, the steady state solution, the relative displacement Z is same, that is sine omega t minus pi. That pi here represents phase angle, indicating the time lag between input vibration and the resulting relative motion. Here we can see that phase angle varies with respect to the frequency ratio R and the damping ratios. Mathematically, the phase angle pi is given by tan inverse of C omega divided by k minus m omega square. Similar to what we did with amplitude response, we can express this phase angle in terms of frequency R and damping ratio. R equal to omega by omega n, damping ratio equal to C by 2m omega n. The graph shows that a plot between phase angle as a function in the frequency ratio R for different values of damping ratio. Observe the trend in the graph. At very lower frequencies, the phase angle is closer to 0 degree, meaning the relative displacement is almost in phase with the input vibration. As the frequency approaches natural frequency, the phase lag increases rapidly, going through 90 degree. At resonance, for any value of damping ratio, everything is converged at 90 degree. The phase angle approaches 180 degree, indicating the relative displacement is almost completely out of phase with input vibration. The damping ratio phi significantly influences the rate at which phase angle changes around the natural frequencies. Lower damping ratio leads to sharper transition in phase, while higher damping ratio results in a more gradual change. Understanding both the amplitude and phase response characteristics is crucial for correctly interpreting the output of a vibration pickup and for selecting appropriate type of pickup for a given measurement application. We need to consider frequency content of the vibration what we are trying to measure and choose a pickup whose amplitude and phase response are well behaved in that frequency range. Now let's see how the principles we have discussed translate into practical vibration measurement devices. We will start looking at the vibrometer. A vibrometer is specifically designed to measure the displacement of a vibrating body. Recall our amplitude response curve where we plotted Z by Y against the frequency ratio R. We observe at frequencies significantly higher than the natural frequency of the seismic instrument, that is omega by omega n is more than 3. Then this Z of t approaches to unity, that is approximately 1. This means that in the high frequency range, the amplitude of the relative displacement is almost equal to Y. Further, we saw in the phase response curve also, at high frequencies, phase angle approaches 180 degrees. Therefore, the relative displacement Z of t can be approximately written in the form of Y sin omega t. Here the pi you can be substituted with 180 degree. Then 180 degree means it will become 1. So Y sin omega t will come into picture only. The magnitude of relative displacement Z gives us a direct measure of the amplitude Y of the vibration. Here sin 180 will become 0. So Z of t equal to Y sin omega t itself. Now a practical challenge arises. To achieve this condition of more than R, a wide range of vibration frequencies we might encounter. So we ideally want a very low natural frequency for our vibrometer, since this implies a very soft spring, low K value and a very large mass. In practice, making the natural frequency extremely low often leads to bulky and less portable equipment. Therefore, the ideal operating principle for a vibrometer relies on this high frequency range. There are trade-offs in the physical design to balance performance with practical consideration like size and weight. We might not always achieve a perfect Z is equal to Y, but the design aims to get as close as possible within reasonable physical constraints. So we will explore different types of vibrometers and the specific design considerations. Let's work through an example problem to solidify our understanding of how vibrometers work in practice. Here is a typical problem we might encounter: a vibrometer with a natural frequency of 4 radians per second and a damping ratio of 0.2. It is attached to a structure undergoing a harmonic motion. If the difference between the maximum and minimum recorded value is 8 mm, we need to find amplitude of motion of the vibrating structure when its frequency is 40 radians per second. Let's break down this solution step by step. We identify the given parameters as natural frequency 4 radians per second, damping ratio 0.2, frequency of the vibrating structure 40 radians per second. The difference between maximum and minimum recorded value is given as 8 mm. This represents the amplitude Z, that is the relative displacement is 8 mm. It meaning that it is the highest and lowest amplitude. That means you can see it is going to be the upper curve and lower curve in the sinusoidal wave. So this is our 8 mm. So 2Z equal to 8 mm means Z equal to 4 mm only. As discussed in the problem statement, we are given with a vibrometer with a natural frequency omega n 4 radians per second and damping ratio is 0.2, which is attached to the working frequency of 40 radians per second. Hence, the R equal to 10, 40 by 4, 10. The amplitude of the relative displacement means Z, we got it as 4. So this Z is 4. Our goal is to find out Y. So we can substitute R 10, damping value is given 0.2. Just we substitute, we can able to get what is going to be Y. That is, after substituting Z value equal to 4, Y equal to 3.9631. That is, we are given with the value of Z equal to 4 means the amplitude of the vibration of the structure is approximately 3.9632. Because the operating frequency is much higher than the natural frequency, see that it is more than 10. So if it is R is more than 3, as discussed in the previous slide, we are getting the very closer value to the actual amplitude of the vibrating structure. This example demonstrates how we use the frequency ratio and the amplitude response formula to relate measured relative displacement to the actual displacement of the vibrating object. Notice, since the frequency ratio is very large, R equal to 10, value of Y is very closer to Z as expected for a vibrometer operating in its ideal range. Now we see another crucial type of vibration pickup, which is accelerometer. While we have seen how vibrometers are designed to measure displacement, accelerometers, the name suggests, specifically designed to measure acceleration of a vibrating body. we recall this equation what we had it in the previous slides, and also this one where z equal to y, okay, whenever the r equal to larger values. If we want to relate this to acceleration, we know that the acceleration is the second derivative of the displacement. The acceleration of the vibrating body, y, it is double dot, we are putting it, is nothing but omega square sine omega t pi. Let's consider the case where frequency of vibration omega is very lower than the natural frequency, that is r is less than 1. It is nothing but r equal to omega by omega n, which is less than 1. The z by y approaches 1. Therefore, we are writing in this form, and rearranging it, we are getting the final equation. The phase lag phi also small in this low frequency range. This shows that the relative amplitude approximately proportional to the acceleration, since it is omega square y. So we are measuring the natural frequency in terms of the measuring part. Images on this slide shows examples of piezoelectric accelerometers. This one is part A. We are having a different physical forms of the sensors which are compact and robust. Here in this second figure, it is cutaway view illustrating internal components of a typical piezoelectric transducer, otherwise accelerometer. You can see a seismic mass, piezoelectric element, and a preloaded mechanism. The vibration causes the seismic mass to exert force on this piezoelectric crystal, which in turn generates an electrical charge proportional to the applied force and hence proportional to the acceleration. Just to see our earlier discussion on vibrometers, we established that they work best when the operating frequency is significantly higher than the natural frequency. However, the present slide I have a different perspective with respect to the accelerometer. There it is a vibrometer case, here it is accelerometer case, focusing at the lower frequency value. See, it is all the R values are less than 1. And the different values of damping carefully chosen between, you can see 0.05 to 0.7. The magnitude remains equal to 1 almost. Now why it is very important? Recall our amplitude response for relative displacement in seismic instrument. If you are trying to measure y using z, if the denominator were approximately should to be 1, then only we are getting that the relationship z equal to r to y. This observation about the denominator being closer to 1 at lower frequencies. A specific damping ratio is actually more relevant when we consider the instrument as an accelerometer. As we briefly touched low frequency range, the output of seismic instrument can be proportional to acceleration of the vibrating body itself. Accelerometers are preferred due to the small size. This is significant advantage in many applications. Achieving a very low natural frequency, which is ideal for vibrometer operating at higher frequencies, often necessitates a larger mass or a very soft spring, leading to bulkier devices. But in other hand, accelerometer can be designed with higher natural frequencies, allowing for a smaller and more robust sensor design. Here I am telling about the difference between the mass of the vibrometer and accelerometer. Accelerometer mass is very less since it is measuring low frequency range, but accelerometer frequency is very high. Vibrometer mass is very high since it is going to measure the high frequency range, but the mass will be very more, so that we are going to get a very low frequency values. So we have to carefully choose vibrometer or oscillometers. Thank you for your attention today. We have explored the fundamental principles behind vibration pickups, focusing on the seismic instrument model. We also discussed how the relative motion between suspended mass and the vibrating body provides the basis for measurement. We specifically examined the characteristics and application of vibrometers. Understanding these foundational concepts is crucial for effectively analyzing and controlling vibrations in various engineering systems. In the next video lecture, we are going to see about how to design these instruments. Thank you, one and all.